Hello and welcome to York Observatory's weekly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alan I. Carswell Observatory located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every last Friday of the month at 7:30 p.m. local Toronto time. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Instagram with the handle at Yorku Observatory and Facebook at Alan I. Carswell Ops. Alan I. Carswell Observatory runs the Astronomer in Residence program in collaboration with Killarney Provincial Park to host astronomers in the certified dark sky site of Killarney. And they lead in-person presentations and shows using the park's observatory. Our current astronomer in residence is Robin Metcalf. If you're interested in learning more about this program or want to apply next year when applications reopen, visit our website at yorku.ca/science/observatory/air. Good evening and welcome once again, everyone. I'm Maheen and I'm one of your hosts this evening along with Boris, Dev, Hector, and Paul. Tonight we have the pleasure of being joined by an amazing speaker, Alan Chan, all the way from the Australian National University, whom we will be introducing shortly. Before we get started with our show, I would like to mention that the observatory at your campus is in Toronto, and we would like to welcome you all to our show and to acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Takaranto has been caretaken by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many Indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts join the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. Next up, we have What's Up in the Sky, and I will hand it over to Boris, who will tell us what's up tonight and this coming week. Take it away, Boris.
I'm Boris, and before we get started tonight, I just want to talk with you a bit about the kind of stuff you'll be able to see up in the sky tonight and in the coming weeks. So we'll start off with the planets. Saturn right now is very visible, especially early in the night, as early as 8 p.m., rising in the eastern sky. Mars and Jupiter are also visible, but they come a little bit later. Jupiter will be above the horizon around 11 p.m. tonight, and Mars will be up a bit after midnight. Venus is visible in the western sky right about at sunset. You might be able to catch a glimpse of it just before it goes out of sight below the horizon. But it's right at the sunset time, not during the night. If you're in a dark enough area, you might also be able to make out the Andromeda Galaxy rising in the eastern sky. It'll be right nearby the lower arm of the Pegasus constellation, if you're not sure where it is. The moon tonight is in waning crescent stage. And if you have a pair of binoculars tonight and the sky is dark enough, then you might also be able to make out the Beehive star cluster right next to it, a couple hours after midnight. The Beehive cluster is a star cluster. It's one of the closest star clusters to Earth. Its official name is Messier 44. It's a collection of 1,000 stars that's 600 light years away. The stars all formed around the same time, roughly 600 to 700 million years ago, which makes them very young, actually, by star standards. Our sun, for instance, is 5 billion years old. If you need help locating it, it'll be right between the moon and the star Regulus, which is the brightest star in the Leo constellation. A little later in the month as well, possibly from the 15th to 17th of October, a newly discovered comet called C23A3 should be visible across Canada. Now, comets are balls of ice and dust that mainly exist in the outer solar system, but sometimes one gets knocked by the inner solar system due to another body, a gravitational interaction, or even an impact. And the heat from the sun as it approaches causes the ice to start vaporizing, and that forms the tail you see. Comets have two tails, a trail that trails behind the comet's motion. That's made of particles that are evaporating off the comet. And secondly, there's an ion tail, which is made up of ionized gas, and that points directly away from the sun itself. So this is a new comet. Astronomers are still learning about its orbit and how bright it'll actually appear in the night sky. So keep an eye out for updates as we get closer to when it'll swing by. Now I'll hand it over to Paul to introduce our guest speaker for tonight.
Hello, everyone. My name is Paul Mack, and I'm a second-year student in the Department of Physics and Astronomy at York University. It's my great pleasure tonight to introduce Alan Chan, who is originally from Toronto, but is now a BSc candidate in the Department of Astronomy and Astrophysics at Australian National University. His research interests include observational cosmology, multi-messenger astronomy, active galactic nuclei, supernovas, black holes, dark energy, and gravitational wave. And he operates out of the Mount Stromlo observatory near Canberra in Australia. Over to you, Alan.
Hi, everyone. Good evening. My name is Alan. I'm a Bachelor of Science student from the Research School of Astronomy and Astrophysics here at Mount Stromlo Observatory and the Center for Gravitational Astrophysics. So tonight I'm going to bring everyone through an excited journey of going through the dark side of the universe, looking at the mystery coming from active galactic nuclei and gravitational wave. But first, I would like to acknowledge the traditional owner of the land that I'm currently at and where Mount Stromlo Observatory is located at, the Ngunnawal and Ngambri people. I pay my respect to the elder past, present, and emerging, and also acknowledge them to be one of the first astronomer of the land, of this land. So quickly go through what am I going to talk about tonight? We're going to start off with a little bit of a topic in cosmology, the nature of dark matter and dark energy. Then we're going to go on talking about two really exciting objects in the night sky, the active galactic nuclei. So those are supermassive black hole in the sky, in some sense of galaxies, and supernova, those exploding stars. Then we'll move on to gravitational wave astronomy. So we will have a look of what we could learn from gravitational wave events, and what could we use gravitational wave plus what we call EM follow-up using a visible telescope to learn about those events, and we quickly go through the future of astronomy. And if we have time, I'll show you some of my experiment I did at University of Western Australia on how do we detect dark matter using crystal. So to begin, here we go. Cosmology, dark energy, and dark matter. A bit of a brief history of our universe. So let's start with the big question, right? In cosmology, what exactly is dark matter and dark energy? Despite it make up the majority of our universe, we actually don't really know what they are. So we up until mid-20th century, most scientists believe that the universe is infinite and ageless. But the discovery of expanding universe, there's a couple of evidence of it. The first one would be the microwave, the cosmic microwave background radiation, which is a really pretty map that show some hotspot around the area where more matter or more activities happening, and they also show some cold spot. So it's kind of like a bit of similar to what the cosmic web would look like. And Edward Hubble also discovered the galaxies, all the surrounding galaxies kind of moving away from us. So this is a bit of a video on how those events is happening. As you can see, the two galaxies kind of merging together and spin off. So this kind of all the nearby galaxy moving away from us is quite interesting to us. We don't really understand why that was happening until we discover some what we call standard candle around. But before we jump into dark energy, let's have a look of what's dark matter and what triggered the search for dark matter. So we have this missing Mars problem. We observe a couple nearby galaxy, Andromeda, for example, and we realized the amount of observable matter of stars or dust is not quite adding up what mass we're expecting it by the rotation speed of the exterior stars. Turns out the exteriors of the galaxy is spinning as far as near the galactic nuclei. So the theory so we have theory of machos, which is massive compact halo astrophysical objects or being born. The theory is there's tiny black holes around the exterior of galaxy. That's why we're not observing those increase of mass and kind of solve the missing mass problem. We actually ran a survey over here at Mount Stromlo Observatory in the early 90s and I think 80s, 90s, and the early 2000s, before our telescope got burned down. Over 11 years, I think we find about 3 machos in distant galaxies. So that theory kind of quickly got moved on, and currently we're on WIMS, weekly interactive massive particle. So those are the prime candidate of dark matter. And so you can see the picture on the left side of the slide. There's some blue stuff in the night sky. So those are actually a simulation of where we think the dark matter is kind of concentrated in those galaxy cluster. The evidence we could see it is by what we call weakly gravitational lensing effect. So when there's a massive object or a massive galaxy right in front of us, lights have to, if lights want to travel past it, actually would get bent by the galaxy, and depends how it's going through. Oops. Oh, sorry, I forgot to share my video. Depend how light is going through those galaxy cluster, it will take a different path. Just because light travel at speed of light, it's kind of constant. If it have to go through a further path, it actually would require more time to do so, and we could observe the delay effect of some really interesting transient object, just like supernova. But we get back to that in a second. The next I want to talk about is dark energy. So here's a Harvard diagram plot on dark energy on the expansion of the universe or the model of the universe using type 1a supernova. So type 1a supernova is this really bright cosmic candle. And on the right side is Brian fighting atom on a, I think it must be a photo shoot, but it's quite interesting. That's why I put it on there. As you can see, they only use several they didn't use too much type 1a supernova to make that discovery of expanding universe, but it's a very interesting discovery and actually land them a Nobel Prize in Physics in 2011. So if I have 3 points in the night sky and wait for a couple billions and couple giga years, what you can see is the distance between them slowly expand, and that would correspond to the dark energy effect on the entire universe and how it's getting pushed away by everything, pushing things further and further away from us. And I mentioned gravitational lensing earlier. Here's a really nice picture by the James Webb Space Telescope of the Harvard Deep Field. And on the right corner there, you can see a galaxy kind of bent out of shape. That one there. So it's actually quite interesting. Just having a galaxy or a massive object in front of the galaxy or in front of stuff you try to observe, light actually could get bent and image could get twisted by that gravitational field. And that actually helped us a lot understanding more distant galaxy using gravitational lensing effects. And and understanding the dark energy distribution or the dark energy distribution throughout time in that case. So this is another really interesting case. So on the left side of the graph, there's 3 circles. So that's a Type 1a supernova going off. This galaxy happened to be behind a decent sized galaxy. So when the first lights came through, there was only 3 supernova came through. But 3 years later, we could see on the right side of the plot the final the supernova light. It's finally coming through after taking a decently long path. So here's a bit of a fun pie chart to sum it up. I quite like chocolate myself, so I figure dark chocolate and stuff will be what matter is. But the scary thing is dark matter and dark energy. It's the majority of our universe, and we could see the effect of them, but we don't really understand what they are made out of. And there's a lot more investigation, either observation or experimental happening right now to try to answer those big questions in astronomy. But that's a bit of a background. Here's what my research is on: active galactic nuclei and supernova. So over here, this is a quasar, emit a lot of it's very noisy. Emit a lot of visible light, a lot of infrared radiation, a lot of UV radiation, a lot of X-ray and radio source. So they're great to look at. So the traditional approach is using Type 1a supernova. So we have a red giant on the right and a white dwarf in the center. As they orbit each other, the white dwarf will slowly eat the red giant to about 8 solar mass, and it go boom. And this brightness is actually could outshine a galaxy, as the picture on the right show. So this is a picture I taken a couple of years ago of a Type 1a supernova. So right in the center is the Type 1a supernova, and on the right side, a bit off center, that's the host galaxy. So when when we be able to observe Type 1a supernova, it actually could go pretty bright. However, it doesn't happen much. For this case, we're pretty lucky because when we analyze the data, it turns out the supernova is about 0.022 redshift away from us. So it's a relatively close supernova. The problem with using Type 1a supernova as a standard candle is we have a bit of a redshift limit. Anything beyond redshift 1.5, maybe 1.6, we don't see much Type 1a supernova, just because the time it takes to make to have a red giant appear and the time to have a white dwarf appear, it's quite long. So being able to use other really noisy object in space to identify the cosmology or to measure distance is very crucial to us. That's why I picked active galactic nuclei as a potential target to look at, just because there's a lot of them, it's all over the place, and they're very, very noisy, which is what we like. The more noisy the sources, the more data we could get out of it. So here's a bit of a diagram of the active galactic nuclei. It consists with a super massive black hole in the center, about 10 to the 16th of a solar mass. But this black hole also have a pretty big accretion disk and some dust around it. That's how it create this light or this energy emitting out of it. So what I do is I use the light or the information coming out from the broadline region, spread out into what I like to call space rainbow or spectrum, and analyze a couple interesting elements that we know is common in those areas. For example, hydrogen gas. Hydrogen gas is very common throughout our universe. Magnesium too is also very common with active galactic nuclei. And for higher redshift, we actually use carbon-4 too. They're not very accurate, but yeah. Here's some more pictures of active galactic nuclei. I particularly love the one that the data gathered by the Event Horizon Telescope team. So over there, I believe is the center of our Milky Way, and just looking at kind of equating stuff is pretty cool. And on the right side, on the left side of the slide, sorry, is a multi-wavelength composite of a quasar or a AGN. You can see radio light it actually emit quite far away from the center of that of the galactic center. It also emit decent amount of X-ray light and visible light. So by studying all those three different wavelengths, you're getting a lot of information out of it. So he says on the right side is a spectrum that or the space rainbow that I took of a active galactic nuclei. And those teeny bumps, well, actually the broad bumps with the green, purple, and blue lines is where we think that the hydrogen gases and the magnesium magnesium elements around the nuclei is. And by using that, we could actually put it into a calculation and a function to figure out how far they are away from us and determine the redshift of those galactic nuclei, which is very important because with type 1a supernova, if you remember from the earlier plot, it only extends to redshift 1. So if we'd be able to extend to redshift 2, 3, 4, or 5, we're getting a lot more information about what our universe is doing back in the day, because the further you look, the older you're looking at, the more in the history you're looking back. So here's a preliminary result of my research. It looks like they're lining up with the current model of lambda CDM. However, it's a bit off at the redshift to 1 area. We believe there is some error with our data taking, so we might have to redo that and figure it out. If not, maybe lambda CDM is not entirely correct in this case, which most likely is not the case. Well, now I'm going to talk a bit in gravitational wave multi-messenger astronomy. So we have we've been using visible light and radio astronomy, visible and radio astronomy for quite a bit. Gravitational wave been theorized a long time ago by Einstein theory of general relativity. However, the first event that we detected is 2014 or 2015, I think. But the fun event that we detected is GW 170817. That's the binary neutron star merger. And I'm interested in those events. So far, LIGO and Virgo and all the gravitational wave people only detected about 94, 97 gravitational wave event. And there's only 2 of them is what we call multi-messenger event. So it doesn't just emit light, doesn't just emit gravitational wave, and actually emit light as well. So the noisy universe is really good for astronomers. I like when there's a violent event happening in space. They usually emit a lot of energy and a lot of information. So for particle, we could have Ice Cube in Antarctica. It's a pretty cool observatory because it's cold. It's also so what Ice Cube does is it detects neutrinos going through the ice cap. So we have light, which is EM Spectrum Observatory. We have the telescope that we can look through using our eyes. There's the radio telescope. There's the SKAO, the Square Kilometer Array here in Perth, in WA, and in South Africa. And we have gravitational wave, where LIGO will be. So what is gravitational wave? Can I surf on it? Maybe, but you won't look as cool as the dog surfing on this board here. So gravitational wave is it's an effect coming from usually 2 massive objects orbiting each other. So for here, I have 2 star-like objects orbiting each other. This kind of gravitational wave, our current detector won't be able to detect them. Just because it's a bit too weak. So the 2nd generation gravitational wave detector can only detect merger or during merger of of 2 black holes or binary neutron stars. So that's the bit of a limit. Having a binary star system just like this and creating the ripple we should be able to detect it with maybe third generation or even using LISA, which is a space-based gravitational wave observatory that supposed to go up in maybe the next 10 to 20 years. It's a collaboration between the European Space Agency and NASA. So like I say, for optical, we have the GMT telescope here. This one here is 38-meter wide. It's in Chile, next to the, it's part of the European Southern Observatory. And for gravitational wave, I have this really interesting plot here. So this is what we kind of simplified version of how a gravitational wave detector work. Essentially, you have a laser going out, split into two half, where we call arms. So currently, LIGO have a 4-kilometer arm. So from the splitting point all the way to the end of the mirrors. So when a gravitational wave comes through, it would actually changes the distance between the arms from 4 kilometers to it's actually very tiny. It's probably around a quarter of an atom. But we're detecting those waves using the property of light, which is the destructive and constructive interference of two light paths. And we get a very loud noise or a very loud result from really, really tiny deviation of light path. So over here is, I think it's Virgo here. And as you can see, the pipe there is actually the arm length. So that arm length it's 4 kilometer wide, and the plot on top of Virgo is a gravitational wave event. This one I believe is a black hole merger. It's very, very bright, as in it create a really, really massive ripple coming out of it. But what we're seeing at the end going up is actually just the merger, sorry, not just the merger, just the collapse or the collision of two black holes. And optical, it's a lot more pretty. It's a lot more nice. You got space rainbow, and you could look through a telescope with it. But however, optical wavelength is quite limited of what we can see. And it's also affected by a lot of hydrogen gas in our universe. So it could get absorbed by what we call cold nebulas. And gravitational wave have that benefit of kind of bypassing a lot of those issues. So here's a bit of a gravitational wave spectrum. From the early fluctuation of the early universe, just like the cosmic microwave background radiation, we could actually use that to kind of see what kind of background noise or what kind of ripple it's created during the Big Bang. And recently, if you have seen the Nature paper or Science, I forgot it's either in Nature or Science, the GW team actually get a publication for pulsar timing. And I think in the next couple of years, they might get a Nobel Prize for that too. So pulsar timing is also a pretty cool way to figure out if there's gravitational wave coming through. Instead of like LIGO a 4-kilometer arm, you're getting a arm as far as the pulsar. So it would give you a regular pulse. Pulsar will give you a regular pulse. Let's say 1 per second. It would be a pretty slow one. But when gravitational wave comes through, that the difference between pulses would actually shrink a little bit or stretch a little bit. That's how we detect gravitational wave using pulsar. Using LIGO would give us rotating binary neutron star and supernovas on the lower end. So we need to have what we call third generation ground-based gravitational wave detector for those. However, if we want to look at binary stars, compact binary, kind of just doing the things, doing the cosmic dance, LISA is what we need to develop, which is 3 satellites floating in space. They're about 200 million kilometers away from each other. And it creates this triangle array kind of just rotating around in space. So currently we're developing a lot of technology with LISA. And the next step from that is to send out three satellite, maybe 4 satellites out in space, and it's 1 astronomical unit apart. So it'll be the distance between Earth and Sun, and that would give us a pretty good coverage of the gravitational wave spectrum. So the goal is to fill this spectrum with all sort of detectors. I also brought a bit of a video for everyone. This is how gravitational wave sounds like. So you can't hear much in the beginning of the audio because we still not be able to detect what's going on before that. But that bit is when the black hole finally merge or close to merging, and those are very quick time scale. So you look at for 1 of a second, and that's all you got to detect it. And once that's done, that's pretty much it. There won't be any wave after that. So it's a bit different from type 1a supernova as a transient object. Gravitational wave is something that you have to monitor essentially 24/7. Here's a bit of a map on where the gravitational wave come from in our night sky. As you can see, the Milky Way kind of look like a U shape here. The problem with gravitational wave detection these days is we're getting a massive area on where the GW event is coming from, but not precise enough for what we call EM follow-up or using an optical telescope to shrink in that area and check out what's going on. If there's a binary star merger, I would love to know there. Love to know that. And if it's within an arc minute, it's pretty doable with 2 or 3 telescope. But if it's within half of a sky, I can't have a telescope kind of scan through the whole sky before the event is over. So with 3rd generation gravitational wave detector, which is the picture is here. Oh, it's a bit pixelated. Oh no. So this is two gravitational wave detector. The one on the left side is Einstein telescope. It's a project by Europe, and the picture on the right side is the Cosmic Explorer. So that's it's similar to LIGO, but it's going to be, instead of a 4-kilometer arm length, it will be 40 kilometers. So hopefully with those new gravitational wave detector coming online, with my research in AGN, using AGN as a standard candle, plus using gravitational wave, we could kind of expand this understanding of dark energy and cosmology a bit further back, maybe close to the first star when it happened. Thank you. Oh, I do have some bonus slide about my my experiment in WA. So when I was in the University of Western Australia, we did a bit of an experiment using this particular crystal in a what we call a microwave cavity. So what we does is we put some electrical charge in there and get it to a resonant frequency, just like a tuning fork. Our theory is when we be able to find the exact resonant frequency, and if there's a dark matter particle, a high frequency gravitational wave happen to come through, it should shift the resonant frequency left or right on this scale, and we'll be able to detect that. So it's a pretty interesting theory, but we still haven't detected anything yet. So there's a lot of effort being done on detecting dark matter, understanding dark energy, and doing more gravitational wave and observation with different objects in the night sky. But thanks.
Thank you so much, Alan, for coming on today and giving us an amazing talk. It was really nice to listen to you today. We do have a few questions if you're willing to answer them. The first one is by Paul.
Yeah, hi, Alan. So many years ago, I was watching, one of the final. I think it was in fact the final space shuttle mission, uh, and they added this extra mission to launch the alpha magnetic spectrometer. It was launched in 2011, and I'd like to know if you can discuss the findings to date. One of the purposes of that mission was to look for evidence of dark matter, and I wonder if you could discuss the implications for the detection of dark matter, which I believe they've been working on since.
Yep, absolutely. I'm not an expert on that particular mission, but from what I could what I could see and read the result of it, it looks like it's to the mission purpose is to detect positron in cosmic ray, and we believe that might be a signature of dark matter or dark matter and anti-dark matter annihilation. So we did find we did find that there's some excess of positron in some active galaxy. It could be dark matter collision, but it could also be produced by pulsars. The data is very interesting. The result is also very interesting. It's been up for 12, 13 years now. I think they're still planning to run it for a bit more. Hopefully with more data, we get more information about would positron emission be actually from dark matter annihilation or some other astrophysical source. But currently we still the jury is still out on that one.
Thank you so much.
Thanks, Paul.
Hi, Alan. I wanted to ask, I've read a few different theories about what dark energy may be and different ideas on what it is and its nature and how it would work. So I was curious, out of all the theories that you've come across, all of the readings that you've done,
Yep.
all the personal experience you've had on the subject, which do you think would be the most plausible explanation for it that we have so far?
I quite like the this cosmological constant type of idea about dark energies just kind of just there, filling up space. There's my colleagues working on or studying on dark energy being a theory of modified gravity. I think it's a bit too much math for me. I don't really understand it, but it's certainly interesting to see how many avenues we're trying to explore here. However, with more recent survey, we're seeing a lot of inconsistency for different survey on dark energy. So I personally think that the theory is a bit we're missing some crucial part on that. And sorry, another theory is also a dynamic field, which energy density could vary in time and space. And currently, I think that's most possible based on the result we are getting. It looks like dark energy is not as uniform as we thought it would be.
Thank you.
Yep, thanks.
Hello, Alan. My name is Dave, and I have some questions for you.
Yep.
Is dark matter evenly distributed throughout the universe, or does it vary in different regions of space?
That's a great question. So we know that dark matter is not kind of distributed evenly throughout the universe. By the look of it, or by the data we have, most dark matter actually would locate surrounding where her galaxy is, or kind of follow this cosmic web. I might not have a picture of that, but if you look at the cosmic microwave background radiation map, there's some hot zone and there's some cold zone. The cold zone tends to have not much dark matter in there either, and not just matter. And we could look at different galaxy cluster in our night sky. For example, the bullet cluster. Dark matter is kind of concentrated in the center, just because when the two galaxies merging together, they kind of stick around there. So likely that it's not distributed evenly, and we think gravity it's also because dark matter is it's interactive with gravity, and um, and gravity kind of matter for matter and dark matter kind of stick together.
Oh, thank you.
Thanks.
Okay, so how do we know dark matter exists if it doesn't emit, absorb, or reflect light?
Cool. So we be able to we're able to detect dark matter the same way that we kind of similar way that we detect black holes. Black hole emit some if it's active, it emit a lot of stuff. Dark matter is never active. So but we be able to see what we call a gravitational lensing effect. So if a galaxy look a bit out of shape, let's say a spiral galaxy should look a this shape, right? If there's a clump of dark matter in front of it, you could actually see the lights being lensed. Another very good example of dark matter exists is the Andromeda galaxy, our neighbor, our closest neighbor. Well, if you don't count LMC and SMC, they're kind of our Milky Way. But anyway, if you look at the rotational speed of exterior stars, they're going a lot faster than they should. If we just count the matter around that galaxy and calculate the rotation speed of those stars, the speed they're currently at, we should actually slingshot them out. But what happened is they're in a relatively stable orbit. So the only logical explanation is, oh, there must be more matter around that area. We just can't see them. So those two are the biggest kind of clue why we think dark matter exists. But if the question is, what is dark matter? I wish I could answer that, but unfortunately I can't.
Thank you.
Hello, Alan. Thanks so much for sharing all this information. I found your presentation really, really cool because the talking about dark side of the universe is pretty interesting. So, well, let me ask you, Alan, can you share any recent discoveries in observational cosmology that have surprised or excite you?
Oh yes. So my supervisor actually just came up with the collaboration that my supervisor is in just came up with this new paper with the dark energy survey, or AUSTAS, the Australian Dark Energy Survey, the 5 years data coming out of it. So that survey is using type 1a supernova and using spectrum to understand the distribution of the universe. So after 5 years, they just release their final cosmology result. What we can see there is, by the look of it, dark energy is not uniformly being applied throughout the age of our universe. It looks like there's a bit of a thermal expansion from the Big Bang. Then the universe actually collapsed a little bit or slowed down a little bit on its acceleration, and dark matter became dominant and increased the acceleration of the universe. And that gave us a lot of motivation to actually do my research on using AGN as a standard candle, being able to probe different region or different redshift, different time scale of the universe, and try to figure out the dark energy distribution at each point. The AUSTAS data or the dark energy survey data is only up to 1.4 redshift. And we're already seeing this a bit of this trend. So imagine if you could go to 2, 3, 4 redshift, that would give you a lot more information about the evolution of our universe. But the finding is definitely very interesting. Looking at there's a potential thing that we could learn from this survey, and with foremost in Northern Hemisphere and DESI coming online soon. I think they already start doing their data taking. We're going to get a lot more new data about cosmology or using type 1a supernova or dark energy distribution soon. So I'm looking forward for the next 5 years and see what kind of result we could get out of that.
Wow, that's pretty interesting. We hope that get all these new data in the next years, as you said, and 1.4 redshifting. That sounds pretty interesting. Thank you, Alan. And yeah, other question from me. How does dark energy influence the large-scale structure of the universe?
Ah, that's a question that I thought about it for quite a bit. I don't really have an idea how to answer it. Other than it kind of just push things away. Um, uh, I had the question of would it affect galaxy formation, or its dark energy is too weak at that time or the point in the universe? Is dark energy a lot stronger in the beginning of our expansion, or it's roughly the same to today? Those are the questions that I still haven't been able to answer that. But on a larger scale, what we can see the effect of dark energy is just kind of pushing everything away. So in the future, in the very, very distant future, and later on, what happened might be in our local group, there won't be any galaxy left. Milky Way or Andromeda, after we merge with Andromeda galaxy, at least I hope that's the name they're going for. It's going to be the only galaxy around the area. And if you look up in the sky, it will be pitch dark, and there won't be any galaxy around it.
Interesting. Thank you so much, Alan.
Yeah, thanks.
So I also have one question. From your introduction, I learned that you're involved at the Mount Stromlo Observatory, and at the AICO, we're actually involved with some research activities. We have research specifically in variable stars. So it made me wonder, is the observatory there also involved with such research activities? And if so, what are they?
I'm glad you brought up variable star. I'm going to read off a little bit. So the observatory been doing a couple of our indigenous astronomers have been doing some research with going back to the older stories around the area, around Australia. Turns out Betelgeuse, it's a variable star. It do go bright and dim every now and then. Turns out about 60,000 years ago, when the indigenous people around Australia, they actually make that observation and had a story about Betelgeuse being variable star. And the research, the understanding coming out of it's our eyes is actually a pretty good tools on observing variable star, which we didn't know before that. But the general research that we do here at Mount Stromlo, we have a lot of radio people, so a lot of radio astronomers. We have galactic archaeologists. We have star metallicities people, a lot of spectrum people. We have people doing cosmology. We also have a separate building right next to the observatory. It's called the AITC, the Advanced Technology Instrumentation Center. That's where they actually develop tools for us to do our observation. Either it's building the mirror itself or building parts for the GMT telescopes, or building for instrumentation. So so we go from a lot of theory, a lot of understanding to some observation stuff, and we also do a bit of a instrumentation. And down on Canberra main campus, I'm part of the Center for Gravitational Astrophysics. What we do there is we develop kind of coding for LIGO mirrors, or for any gravitational wave detector mirrors. Try to learn about all sort of noise we could get from those detection, because we're detecting very tiny fluctuation in space. So if a car drives past, it actually could affect that too. Funny story, they actually discovered a bunch of gravitational wave events earlier this year. Turns out to be a rattlesnake in LIGO. So they're very, very sensitive stuff. The group that I'm studying under is the space group. So what we do there is we develop understanding or laser tracking system for spacecraft, just like the GRACE missions. So that's that's two satellites flying in space with a laser link. What it does is go around Earth, and they try to understand the shift of mass. So it started off in, I think it's 2003, and now it's the GRACE follow-on mission. It's the second generation of the mission. And what we can see is actually there's a lot of ice being melted in Antarctica and Greenland, and we could see a general increase of sea level using those experiments. But that kind of technology also translates to LISA, for example, the space-based gravitational wave observatory.
Wow, that's some super interesting stuff. Thanks for telling us all about it, and I hope we can visit the observatory sometime soon.
Absolutely.
Thanks again, Alan, for joining us tonight. I will now hand it over to Hector to say goodbye to everyone for the night.
Well, everyone, you have been listening to the Alan Carswell Observatory monthly TeleTube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Boris, Dave, Maheen, Paul, and myself, Hector. Thanks everyone for joining us tonight, and a special thanks to our speaker, Alan Chan, for a fantastic talk about the dark side of the universe, and also for answering all of our questions. All of our programs are free, but if you would like to make a donation, see our website at yorku.ca/science/observatory/. You can always connect with us on Instagram with the handle at Yorkie Observatory, on Facebook at Alan Carswell Ops. Also, check out to our website for show notes, content, updates, and contact info at yorku.ca/science/observatory/. Thanks for tuning in. Clear skies and have an excellent night.